This is joint work with Ashish and Ajil, who are our students in UT Austin in computer science and electrical engineering departments, respectively, and Eric Price, who's a faculty member in CS in UT Austin. So this is the outline of my talk. So I will be talking about generative models, specifically GANs and VAEs that we will be using. Then I'll talk a little bit about compressed sensing, which is just linear tomography. I guess I don't have to say a lot to this audience about that and why is that important. And the punchline of this talk is that you can use GANs, generative models, as priors for compressed sensing. That's sort of the third punchline here. So then I will tell you the one thing we can prove. So there is one theorem that we can get under several assumptions, of course. And if given time, I'll talk about the proof techniques a little bit. All right. So generative models, there is basically feed-forward neural networks that take a vector, a low-dimensional vector z. So I want you to think of this as a vector in 100 dimensions. And there's here some crazy neural network that has a bunch of layers that have convolutional layers, as Stefan described this morning. And there's a bunch of weights here that you learn. And after you have learned them, you have basically learned a continuous mapping, differentiable mapping from 100 numbers to arrays that are 64 by 64 by 3. Let's say this is red, green, blue, 64 pixels by 64 pixels. So it's a very big 13,000 dimensions, let's say. So these weights can be trained. So if you put here some random Gaussian vector, you get on this side an amazing image of whatever you're trained, like Stefan showed, of a bedroom or of a face or of a cat or whatever you're training it on. And there are two ways that you can train these generative models. You can train them with standard maximum likelihood techniques. And depending on how you set it up, you get what's called variational autoencoders that make nice images, but not quite as spectacular as they have been done in the last months. Essentially, last 6 months have had the breakthroughs here. And then the fanciest, newest thing is these things called GANs, which use this idea of, instead of having a fixed loss function like maximum likelihood, the loss function itself is a neural network, another neural network that we call the discriminator, and you train the loss function concurrently with the generator in a competition way. And that's like this amazing new idea that started by Goodfellow et al. Paper. The only thing I will need in this talk is that people with enough data can train these models to dream of faces or cats or bedrooms. And don't worry about how you train it, that's another talk. But after you have these weights in this neural network here, this is all I care about is that this is a differentiable function from this to this. So I can ask, if I modify this scalar, how much does this vector change? And I can compute a gradient. And that's all I will need. And that's a pretty magical thing, turns out. So how training a GAN looks like, I'll just show you. So there is a number of layers here that start from a low-dimensional 100 vector, and through a number of, the first layer, as Stefan showed, is typically a linear transformation and a ReLU, and then there's a number of convolutional layers that make it bigger, and neural nets people call these deconvolutions, which have nothing to do with deconvolution, of course. It's just a convolution that actually just simply expands, okay? So the architecture that we will be using here is a specific deconvolution architecture. It's called DC-GAN that produces, that looks at faces and starts to try to dream of things that look like faces. So here, this is from my lab. I will be showing you how, as we're training this network, it starts to become better at dreaming up of faces. So initially, it makes this thing which looks kind of like a face. But as you train it, it makes better and better and maybe better. But then after a while, you're not even sure if it's better or not. Depends. And then at some point, you stop. And there's a million heuristics about how you stop, how you pick your step sizes, how you adjust like all these parameters to make this thing actually work. And it takes good grad students weeks to actually train this stuff. But if you put enough effort and enough TensorFlow and PyTorch hacking, you can do that. And the thing is, this is a face, but this is not an actual person. This is some random, you just put here 100 numbers, and through these weights, these numbers come out. So that's amazing, right? And I'll be just showing you a batch here of GAN training where it starts pretty bad and it increasingly gets pretty good. Okay? So the other thing that Stefan also mentioned is, and that's key, is what's called mode collapse. Mode collapse means maybe this thing, by the way, the training here is done on a data set called Celeb that involves 60,000 faces of celebrities. Maybe this thing has just memorized pieces of images, or actually even faces, and just shows me one of the things it has memorized. How do I know that? So one of the sanity checks is what's called z-space interpolation that Stefan also showed. So you start with your favorite vector z, like 1, 0, 0, 0, and then you pick your second favorite vector, which is 1, 2, 3, 4, 5, up to 100, and you do linear interpolation between these vectors in z-space, and then you go, each one of these vectors, you take it in g of z, which is an image, and you look at the images, right? And if you see face, random noise, and then only at the end another face, you're worried because it has just memorized two faces. If in the middle you keep seeing natural faces, it means it actually has learned something more than just memorized faces, right? So here I have a linear interpolation that we get. And you can see that it interpolates smoothly, and all the things in the middle are actual faces. So we're traveling on the manifold of natural faces here. Okay. And this is sort of the latest flavor of GANs called big GANs that have a different way of defining the discriminator, and they produce amazing results, okay? So you can pass a Turing test here where you show someone, is this a real person or a fake image, and you won't be able to tell the difference, okay? They also are all very good looking, but that's because it was trained on celebrities, you know? So, so we can't compete with that. The punchline is, and if you go to NIPS and ICML, this is we jokingly call this now as a beauty competition, because when you get a new GAN paper, you don't even read the paper, you go directly to the images, and you know that's a big factor if the paper will get in NIPS and ICML. So, but you know this kind of has to stop at some point, because you're like, okay, it's all good, but we can get amazing images, and we can train this on cats and bedrooms, and people have done all this stuff. And they get better and better, like very fast. The past 6 months has been amazing. But what can you do with that, okay? That's cool, but you know, what can you do with it? So here, my punchline is you can do compressed sensing with that, all right? Which means you can do tomography with that, all right? So compressed sensing simply means linear tomography. What does that mean? I will take the simplest setup that is still interesting. And the simplest setup that's still interesting is you have a vector. I don't know if you can see it. It's a little... not very, so this is a vector that let's call x that is in n dimensions, so I'm using compressed sensing notation here, but you don't get to look at this vector, you don't know this vector, you only get to look at linear equations on the vector. This is what you get to look at, measurements, and the number of measurements is m, right? This is standard compressed sensing notation, and you observe linear equations and you want to recover x. And of course you cannot recover x from linear equations because you don't have enough linear equations. So you know, even a child in kindergarten knows that if you have, you know, 100 unknowns with 50 linear equations, there are infinitely many solutions, right? So it's a nil-post problem. So of course there's many variations when there's also noise, and then you can do other stuff too, but let's just take even the noiseless linear equations problem. So there are many solutions. Which solution do you want? And the answer is you have to impose some prior information about the most natural solution, of course, as many people described. And what you define as natural is the key in solving these ill-posed problems. So the standard assumption in compressed sensing, of course, as most of you know, is we assume that this vector is unknown but sparse, right? So there are only k non-zeros. And then we would like to solve this problem, which says, hey, out of all the vectors that satisfy my linear measurements, please find the one that is the sparsest. Okay, that's the L0 norm. Unfortunately, this is a combinatorial optimization problem that's provably NP-hard. So you will never be able to solve that in general. So the standard thing that people do is they relax this L0 norm into an L1 norm. And this problem now is called basis pursuit. And you can show it's a linear program, so you can solve it efficiently. And the key mathematical question is, under which conditions on the matrix A will the solution to this thing, which I can get, will probably be equal to the solutions of this thing, which I cannot get, right? And of course, obviously, if the matrix A is full rank n, there is only a single solution to this set. So you can optimize whatever you want, and the optimum of this would be the same as the optimum of this. So this problem is interesting when you want to have a few measurements, right? So the question is, how few measurements can you have and still recover the correct thing? This is in the theory of compressed sensing. If you, instead of having exact measurements, which is this, you had noisy measurements, you would say, I want this minus this L2 norm to be small, and then you'd get another super famous algorithm that I'm sure many of you are using, that's called lasso, right? So basically, the lasso is the relaxation of this. Great. So there is a lot of work on this, of course, going back to the very famous papers by Donoho, Candes, Tao, Romberg, etc. Rice has many people who have done pioneering work, of course, on compressed sensing from Rich's group. And there is the punchline, and I'm telling you this because I want to use it later, is there are conditions on the matrix A that's called restricted isometry property is the most well-known, and there are other flavors of this. One's called restricted eigenvalue condition, which is essentially the lower bound of RIP, and another condition called null space condition that prove to you, and there is nice theorems that say, oh, if my measure matrix is nice in this sense, when I solve this problem, I get the same solution as this problem. Okay? And the second very nice thing is how do you get matrices with a few measurements that satisfy these technical conditions? Oh, you just make them random, okay? So you just make Gaussian random matrices. That's one of the very famous theorems. And if you make the number of measurements to be k log n over k, so the notation here, k is the sparsity, n is the ambient dimension. So k is the smallest possible number of measurements you could ever hope to get, of course, when you have k unknowns in some unknown positions. This tells you k log n over k measurements suffice with high probability to provably solve this and get the solution of this, which is very nice. So a random measurement matrix with enough measurements suffices for the linear programming relaxation to produce the exact unknown sparse vector. So this is all well-known stuff in the theory of compressed sensing. Now, this is my motivation. When on earth do you have a problem where you have an unknown vector and you see linear equations on its entries, but you don't get to look at the vector? Of course, in this audience, this is, I shouldn't be asking this question, any tomography problem is this problem, right? Or any linear tomography problem is this problem. So you have a brain or something, and you want to look at the values of the pixels in the head, but you don't want to open the head, right? So what you do is you shine some light or some X-ray or some physical process that, for many physical processes, computes some linear equation of these unknown pixels to you. These are linear tomography problems. Or it could be a nonlinear functions of these, which is even harder, and we'll talk about that in a minute, right? So the other observation is that real images, of course, are not sparse, except the night sky, which has only dots. But many real images are sparse in a basis, right? So if I know the basis, and I use, let's say, a nice basis, like a wavelet basis, or a DCT basis, then that's a very good approximation for real images. So you can use that and get good results using lasso for compressed sensing for natural images. So what is the punchline of this talk? So in this talk, I'm saying sparsity is great. It's a decent model for natural images. But now we have these much better, fancy data-driven models named VAEs and GANs. So how about we use these fancy new models, take sparsity out of compressed sensing, and replace it with a GAN. So that is what I'm proposing here. Okay, so how do I do that? How do I use a GAN instead of sparsity in compressed sensing? Okay, so it's a simple idea. I say the vector that you have that is unknown, before you were telling me it is sparse. Okay, now it's not sparse. I tell you there is a GAN, a neural network that is fixed. It's trained. And there is some Z star that produces G of Z star that is the vector you're looking for. Now I want you to, you observe linear equations on this vector, I want you to reconstruct the vector. And you have this. You have a generator for the type of data you are working on. All right? So if you're working on faces, which I will be, you're working on, you have a GAN. If you want to work on MRI scans, which is very hard, but there's a million people right now working on that, right? If you have a trained GAN for the problem you want to sense, you can do amazingly well sensing, okay? So now what I'm trying to communicate is how will you use this neural network for your sensing problem? That's my question. All right. So, oh, and I have a question here. Before you had sparsity, the number of non-zeros of x. So I am replacing sparsity with a neural network. To recover before, I was using lasso. What is the recovery algorithm now? That's the question. All right, so we're going to discover the recovery algorithm together right now. So let's warm up. So the only thing you have when you have neural networks is backpropagation, okay? Gradient descent. That's the only magical thing you have to learn is this. So after you learn this, you cannot unlearn it. Everything you're going to think about will be coming with that language. So let's do that. So warm up is, let's just say that I had perfect observation. So my measurement matrix is identity. So I see all the pixels, let's say it's of this phase. And I'm asking myself, how can I find a z so that g of z looks like this woman, okay? How would you do that? You will write a loss function, and you're going to do gradient descent. That's always what we're doing. So what is the loss function? Well, we're going to make a loss function not in the weights of the network, because people spend blood and sweat to get the weights of this network and the weeks on GPUs. We're not messing with the weights. We're keeping the weights fixed, and we are changing z. We're searching in z space, right? So we are simply going to write this nice little loss function that says, I am looking for a z so that the image that this network dreams looks like the target image, okay? So this is a loss function in z. I start from some random z, 1, 2, 3, 4, 5, up to 100. This is a differentiable function of z, and that's the key. And I can compute this gradient because I use backprop through this machine. And I do gradient descent, and I update my z. And that's how I reconstruct this image from this image. Is this making sense? Okay. The key thing is, how do you find this 100-dimensional vector? Searching over 100-dimensional vectors, that's the number of vectors you have to search is exponential in the dimension. Okay? So you do gradient descent using this loss function. Okay, good. This was discovered in our paper. Of course, it's kind of obvious, and many other people have discovered it too, obviously. But let's see how this idea goes forward. Okay, now we want to solve in-painting. In-painting can be seen as a special case of compressed sensing, where the measurement matrix is, of course, you had the identity before, but you lost these pixels, okay? You know which pixels you are losing, which corresponds to just dropping some rows from the identity, right? So that's your measurement matrix now. How do you solve this problem using my idea? Now I want you to invent the algorithm. It's almost the same as before. Before it said, find a z so that g of z looks like this, okay? And do gradient descent of that. Now, do you still want this network to dream of a face of a woman with a huge black square in the center of the image? No, okay? You want to make this network dream of an image of a woman that looks like this woman, except on the center where it can do whatever it wants, right? Okay, so you can write a loss function for that, right? That's just simply saying, okay, A times g of z is the measurements, right, which is just dropping some pixels. And I say the pixels you get to observe look like the observed pixels. And that's just a bunch of linear equations. This is a differentiable function. You do gradient descent in z. Does that work well? So I'm going to show you our result for this image from our paper. So this is the woman that it dreams, which is pretty good, I think. Now, observe a few things, that even the mouth changed. Why did the mouth change? The mouth changed because this gun cannot dream of a woman that perfectly agrees with this woman on the boundary, right? Well, if tomorrow somebody makes a better gun that can dream of, so if an ideal gun should be able to do that, because this is a real picture, right, of a real person. So if it was the ideal gun that had learned every possible face, it would perfectly agree here. And I'm telling you, if you give me a better gun tomorrow, I will get a better reconstruction, right? Next step, super resolution, possibly also called deblaring. All these problems are things people talked about today. Okay, you see a face of a blurry woman, okay? What is your algorithm to do super resolution using the same idea? Are you looking, you search in Z space, you have to give me a loss function, right? What's the loss function? So yes, so you don't want of this network to dream of a blurred woman, right? You want this network to dream of a woman that after she has been blurred, looks like this blurry woman, right? Yes. Okay, here I know the blurring operator, which is sort of cheating, but so were all the previous speakers. Yeah. Okay, you know what? If you don't know the blurring operator, you search over blurring operators, of course. You do something else, right? But yeah, here we assume we know the blurring operator, which is just saying, this pixel is just the average of these 5 pixels. This pixel is just the average of these 5 pixels, right? It's just a matrix, okay? It's again another measurement matrix, all right? So my algorithm is again define this loss function that is blurring the dreamed image, and I want the blurred dreamed image to look like the observed blurred image. That's a loss function of z, start from a random z and do gradient descent in z using backprop because you can backprop through this machine. And that's the magical thing. Okay? Yeah. Backprop is an algorithm that uses chain rule, but if you naively, so backprop is essentially an algorithm that allows you to compute gradients of the input of a feed-forward neural network with respect to the output. It is using chain rule, but it is non-trivial, because if you trivially think about opening chain rule, the number of paths is exponential. Okay? So the fact that you can do chain rule is a non-trivial statement. It actually uses dynamic programming in a highly non-trivial way to compute the gradients of the input with respect to the output. It's not a trivial thing. And it's also been optimized to death in TensorFlow and PyTorch, which allows us to actually do that. So that's the driving horse of all this technology. Great. So this is the blurred image, which I think is pretty good. It's not actually the original person, but it's pretty good. And if you give me a better GAN, it will be better, right? So the general algorithm says, okay, you have a GAN. The GAN makes an image. This image is multiplied by a linear operator and gives me a few measurements. I say search in Z space so that the measured G of Z agrees with the measurements as much as possible. You're only searching in 100 dimensions. You're not searching in the dimensions of X, which is 13,000 dimensions, right? And you search using gradient descent. That's a general algorithm. So, and the key idea, as we discussed many times, is you can obtain useful gradients in this low-dimensional space because of backprop. Okay, let's compare to Lasso, one more experiment. So Lasso, so here we're doing compressed sensing with Gaussian IID measurements. It's a standard thing. And here, these are the original images. Here I'm showing you what Lasso gets if you assume sparsity in the discrete cosine transform, or if you assume sparsity in a wavelet basis. And here is using our method. And of course, we know much more about images, right? Because Lasso says, the only thing I know is I'm searching for something that's sparse in DCT. But I have, like, this thing has seen 60,000 actual faces, and it has learned much more about them. That's why we do much better. So this is the actual plot. So because we don't actually fully do much better, let's be clear. So the performance of our algorithm, just two variations. Here we added some regularization. This is the number of measurements, and this is the reconstruction error. We basically need about 10x fewer measurements compared to Lasso to get same performance until at some point it stops getting better. At some point, our algorithm doesn't actually give better and better images. Why is that? The training size of the GAN. Yes, exactly. So the GAN has some representation ability, okay? The GAN says, okay, this is the best person I can dream, even if you gave me all the measurements, even if you gave me the full image of the original person, the GAN cannot dream of exactly that face. It can dream of the closest possible face. So here at this point, you have basically reached the representation ability of your generative model, and extra measurements no longer help you. So Lasso after a point is indeed better, because Lasso allows you to match, more things. So what you should be doing if you get to this point is replace your GAN with another GAN that has bigger Z. Right? You have reached the representation capabilities of your generative model, essentially. So we don't always beat Lasso for many measurements. We beat Lasso for a few measurements. Okay? And the number of measurements depends on the Z, the dimension of Z. Okay? This is pretty exciting. So I want to show you that you can use this algorithm even if you have nonlinear measurements. Okay? You may see this already. It's kind of obvious. So instead of having a matrix multiplying your image, You can have any operator you want as long as it's differentiable, okay? And as long as it's differentiable, you can apply exactly this algorithm, and backprop will backprop through this operator and through the GAN and give you directions in Z-space, okay? So I'm going to show you a fun application of that. So let's see what we're doing. So this, I don't know if you know this guy. He's my friend. He's a professor at MIT. So I was giving the talk at MIT, and he was my host. So he, yes, you will wait, and you'll see. Yeah. don't go there. Okay. So here's what I'm going to do. I am going to define this loss. So his name is Kostis, okay? So I'm going to define this loss function, which says I want a neural network to dream of a face that looks like Kostis. Okay, that's okay. That's a first test. But I have also trained a gender detector. That's another neural network that takes an image and tells me the probability it is a man. Okay? So I can train that offline. I take 1,000 images of men and women, and I can train a neural network that produces a single scalar output that says if you put a man, it says 99. If you put a woman, it says 0.1. Okay? And now I am starting from a random z, and this is my loss function. So if lambda is 0, I am trying to find the best possible representation of Kostis in the GAN range, right? So and that's another test to check if the GAN has memorized images or not. Because if the GAN can make an image that looks like my friend, that's very good news that it hasn't overfitted, right? It hasn't mode collapsed. But then, as I'm changing lambda, do you understand what's going to happen? It's going to prefer to dream of images that first look like my friend, but also are women, right? So as I'm changing lambda, this thing is influencing the directions of this gradient to move towards women that look like my friend. Yes, sure, yes. And I'm going to vary lambda. So you're going to see for very small lambda, you get this, okay? And this is the projection of Kostis to the range of the GAN. And as I'm increasing lambda, you see? So you get basically moving in the direction of faces more towards the female space. And this is really fun because if tomorrow you come up with another concept like has a mustache or is good looking or whatever you want, if you can go offline, train a classifier, okay, plug it here, it's a plug and play, and use this box to get directions in Z-space. Of course, if you try to convert my friend into a cat, which I have been trying to do, I really am, it will not work because this GAN does not dream of cat people, right? So this GAN only dreams of people, men and women. That's why it worked and gave a woman, but it cannot produce cat people because there is no data set of cat people. Making that's actually one thing I'm actually working on is how would you get a GAN that can do things like that. But right now there is no GAN that dreams of stuff like that, so I don't know how to do that yet. Okay, this is all nice and fun. Can we actually prove something? Because that's also nice. So what I'm going to basically tell you is that, okay, so I said this recovery algorithm can do, let's say, 10x less than lasso for a few measurements. But can we give any theoretic guarantees? So I'm going to say under the maximum likelihood decoder, which means assuming you could solve this problem, right? Minimize in Z space AG of Z minus Y is a non-convex problem, right? So in general, you can easily prove it's NP-hard. So I'm going to say if you could solve this problem, I'm going to say that if you have a correct measurement matrix, which will be like RIP, somebody mentioned that. So I need the concept of RIP for a GAN, right? So I'm going to tell you what we define as an RIP for a GAN. And if you have that, we can prove that the maximum likelihood decoder gives you good approximation. Restricted isometry property. So this is the classical thing used in the theory of compressive sensing. So I'm going to extend that from sparsity into GANs. That's basically the theoretical contribution. Okay, and the way we call it is set. So the actual property we use is restricted eigenvalue condition, which is a flavor of RIP. And we extend it into something that's called set restricted eigenvalue condition, okay? Because we work now on sets, things produced by GANs, not sparse vectors. All right. So I want to say at this point that there is significant prior work on all this stuff that I'm talking about. Learning manifolds and compressed sensing on manifolds and model-based compressed sensing is not things I came up with. There has been a lot of work by many people, including Rich and other people here at Rice, Mike Wakin, and many people that I'm citing here. So a lot of work has happened before, but what I think is novel is the use of actually a GAN and the specific reconstruction algorithm that uses backprop in Z-space. I think this is through the measurement process. I think that's essentially what is new here. But there's a lot of work on compressed sensing with prior information, of course. OK, this is our main theorem. So let's read this thing. So I'm saying G is the generative model that goes from k dimensions into Rn. K is 100, n can be very large. And I say, let's assume here that A, which is the measurement matrix, so the measurement matrix is m by n, m is the number of measurements, and the number of measurements I will need, that's key. What's the smallest number of measurements you could hope to get? Well, you're trying to get a vector in k dimensions, right? Because that's the z you're trying to get. So k is the smallest possible thing you can hope for. So I am saying you need k times d. What is d? D is the depth of the GAN, okay? What is n? N is the ambient dimension, okay? So I say you need k times the depth of the generative model times log n measurements. And if you make your measurement matrix Gaussian IID, again, then if you could solve this problem optimally, you get a provable approximation error in the reconstruction you get. This is the theorem. So let's open up the terms. So let's look at the terms one by one. So what is the first term saying? It's saying that, what is this? This is the best possible z that the GAN can dream, okay? So this, is this making sense? This is limited by how good your GAN is, all right? The second term is coming from the noise in the measurement. So I described things for noiseless linear measurements, but we actually do it with noisy, with lasso, okay? So this is noisy linear measurements, and you are supposed to be solving this problem, but we say, okay, even if you can't solve this problem perfectly, you have an additive epsilon error in solving this problem, you pay here for that. So this term is how well you do in this problem, this term is how good is your GAN, and this term is what's the noise of your measurements, okay? And this assumes a Gaussian IID matrix. Okay, let's understand the proof. So, okay, so I have another flavor that's, let's keep that. Okay, so I'm going to start with how lasso proofs work, okay? So if you're familiar with lasso proofs, and there's been a lot of work on that, typical proof says, okay, a random Gaussian measurement matrix is good. What does good mean? It has this restricted eigenvalue condition. So RIP, RIC sort of means the same thing informally. We'll get, if you want technical details, we'll get later. I will explain what this means basically, but let's say for now the proof has two lemmas. A random Gaussian measurement matrix is good, and then lasso works if the matrix is good, okay? That's sort of the proofs of, all the proofs of standard compressed sensing follow this architecture, okay? So now we're going to follow the same architecture, but instead of using RIP, we'll use a GAN RIP that I will define. And so the structure of our proof is, if your random Gaussian measurement matrix has this set restricted eigenvalue condition, that depends, of course, on the GAN. Sorry, the first thing says a random matrix has this set restricted eigenvalue condition, and the second one says if your matrix has this set restricted eigenvalue condition, the optimum of the squared loss minimization produces a z hat that's close to z star. Okay? These are the two lemmas I need to prove. Are we happy? Okay. So click OK. Let's understand what is this restricted eigenvalue condition. No, wrong button. So let's understand what is the restricted eigenvalue condition and why do you need it. So in this problem, now we're back in the theory of compressed sensing. If you're solving this kind of problem, what I need you to understand, if you don't know it already, is that if there is a sparse vector x in the null space of the measurement matrix A, you are screwed. Okay? Do you understand? This is just for the standard case of sensing a sparse vector. Because if there's a sparse vector in the null space, you see zeros, and you're blind to that sparse vector, and you're screwed, right? So basically, all these conditions essentially say there is no sparse vector in the null space. That's when a matrix is good. So that's what all this RIP and RAC stuff mean. So now, more technically, all approximately k-sparse vectors are far from the null space in the L2 sense. That's the actual definition of the restricted eigenvalue condition. But now, we do not care about sparse vectors. We care about vectors coming from a GAN, right? So in order to correctly translate this for GANs, perhaps you would like to say all vectors that are coming from the GAN are far from the null space. Maybe that would be what you want. But that's not correct. And the reason it's not correct is that there's an unfortunate coincidence that I'll write here. This unfortunate coincidence is that the difference of two k-sparse vectors is 2 k-sparse. You know that, right? But at most cases. But the difference of two natural images is not a natural image, right? So that unfortunate coincidence is what confuses the definition. So the correct definition for restricted eigenvalue condition is actually any two k-sparse vectors should have the property that their difference is far from the null space. Okay, so this is actually this is equivalent to the previous thing for sparsity, of course, because of this fact, modulo the factor. But for naturalness, it's not true, right? So the correct property that you need to have recovery for GANs is exactly this, but replace k-sparse with coming from the GAN. So this is the actual set restricted eigenvalue condition we define. We say a matrix A satisfies set restricted eigenvalue condition if for all x1, x2 in the set of natural things you want, which are things spanned by the GAN, their difference, the measured difference is far from the null space. Okay? So that is the set restricted eigenvalue condition. And many people have defined similar things for other manifold type of concepts. So it's a very natural thing. If you know these proofs, it's a very, very natural thing, and many people have done very similar stuff. Okay, so that's good. The second thing I need is that if you make a random matrix, you will have this property, right? So how is that? So I have to prove that, and then I have to prove that if your matrix has this set restricted eigenvalue condition, then solving this optimization problem gives you a z hat that is close to z star to prove my lemma. Is this making sense? All right. I want to discuss for a minute this thing because that's the most interesting novelty. The way we prove this is we basically take z space, we make an epsilon net of the z space. So we cover this 100-dimensional unit ball, and then we think of g of z as a transformation that goes from 100 dimensions into 13,000 dimensions. And what we need is really a bound on the Lipschitz constant, okay? If you tell me that the Lipschitz constant is not too big, it means that a good epsilon net here is going to produce a good epsilon net here, right? And then we're union bounding over the size of the epsilon net here, and that dictates the number of measurements we get. I want to tell you one more thing, last thing, because I think it's very important. So I want to talk about adversarial examples because this hasn't been discussed, and I think it's very important. So as I told you, as many people before me said, there are other neural networks that are called classifiers that are very good at looking at the pixels and telling you if this is a cat or not, okay? So in ImageNet, for example, a previous speaker said that they show superhuman performance and all that. So what I want you to think about is that this network can also give you the gradient, right? So you can try to change the pixels to modify this label, right? So this is my friend again, and as I told you, my purpose has been to turn him into a cat, but I don't have a GAN for cats. So maybe instead I just take a classifier for cats that looks at the pixels, and I compute the gradient with respect to every pixel to maximize the chance of cat, which I can do because I can backprop through this thing, and I can update the pixels of the face of my friend to increase this thing, right? Is this making sense? Okay, do you know what's going to happen here? So what's going to happen is do you even see the difference between these two images? There's tiny difference. There's like a tiny little noise, like a little imperceivable noise that you can add to this image and make this classifier think that the probability of cat is 99.8. So this is a very important thing because it shows you that classifiers are extremely fragile into adding this carefully placed dust that is not even humanly perceivable, but is actually extremely problematic for classifiers. So if you're going to ship a classifier, you better, and that's why people have done now, they make these stickers that you put a sticker on a stop sign and the neural network thinks it's a banana, right? Have you seen these things? Yeah. Seriously, yeah. So if a human, I'm not sure they really do that. So these networks are extremely fragile into perturbing the pixels in an imperceivable way. So I'm asking the question, why did this not happen before? And it happened now. And the answer is, before, we weren't doing gradient descent in X space. We were doing gradient descent in Z space. And we were restricting ourselves to be on the manifold. Whereas now, we just use this classifier to get the gradient, but we left the manifold of natural images, because this dust has moved us far from the manifold of natural images. So we defined compressed sensing for images coming from generative models. It performs pretty well for few measurements, but Lasso is more accurate for many measurements. Better loss functions, of course you can combine this idea with Lasso to get even better performance. You can do, of course, I'm not saying, I didn't optimize anything here. I just said this extremely simple idea works really well if you have a good GAN. That's all I wanted to say. Of course, you can do better, and people are working on doing better. The theory of compressed sensing extends very naturally to these set restricted eigenvalue conditions, and that I think is pretty interesting, and there's a lot of things to do. The algorithm can be applied for nonlinear measurements, very, very interestingly. So you can plug and play with different differentiable boxes. I want to say here that the optimization problem itself, I'm never proving anything about the hard optimization problem, right? I'm assuming that if I could solve this problem optimally, I can prove something. Proving something about gradient descent, which is the actual algorithm we use, is extremely interesting. And actually, some people from Rice, Paul Hunt, who I haven't met but I want to meet, has posted an archive preprint on analyzing our algorithm, assuming some things about the weight. So there's a very interesting work to be done in analyzing gradient descent for this, but I did not do that. I just said if you could solve it optimally, then you get guarantees. Okay? And if you have better generative models for something you actually want to sense, then you can do very good sensing. That's the punchline. And the other thing is, go to our GitHub repo where we have trained generative models, trained GANs, because training them is very hard, right? So if you download the trained one, you can do all these things and any other things you want, just using the trained GAN as a black box.